Another momentum problem. This is what I call a ballistic pendulum type problem. A ballistic pendulum is something that's used to measure the speed of a projectile, like a bullet, and the bullet is fired into a pendulum, and the two become one, and then the pendulum swings up and comes to a stop, and you can do some measurements and figure out the speed of the bullet before it hit the pendulum. You probably have a lab on that. There's probably a really nicely worked out example problem in your book with that situation. So I'm not going to do that one, but I'll do something very similar. If you flip to the back of the momentum chapter in any physics textbook, you can probably find 3 or 4 or half a dozen problems just like this, because there's a collision and there's something that happens either before the collision or after the collision or both. So in this problem that we're working, we have to look at what happens before the collision, what happens after the collision, and what happens during the collision. So remember, a collision, 3 ways to think about it. One is 2 things stick together. That's a collision. Another one is that things bounce off each other. Or one thing becomes 2, right? It explodes, it blows up, it pushes apart. One thing becomes 2, that's also a collision. And if any of those things happen, if you have a collision, you probably cannot use energy to get through the collision, because it's unless you're told that it's elastic, and then you can say, oh, my mechanical energy before and after is the same, I can just ignore it and go right through it with energy. But that's not typically the case. Typically it's inelastic, and we can't get through that with energy, because some of our mechanical energy goes into deforming the objects or goes into sound and heat and other things. So we can't typically go through a collision using energy. So what I've done here, I've drawn 4 pictures. The first picture is my initial condition. The initial state of the system. I'm going to call that 1, and that way I can just put on here. This is going to be V1 for, I'm going to call this cart A, and V1 for cart B is also 0. Nothing's moving here. We're going to release cart A from rest, and it's going to slide down the hill, and in my case 2 here, my condition 2, this is the split second before the collision. Just before the collision. And so cart 2 here, cart B at condition 2 is not moving, and cart 1 here in keep mixing these things up, sorry about that. Cart A in our time 2 has some speed that we don't know, but it's moving, and it's moving to the right. And in condition 3, time 3 here, they've stuck together. This is just after the collision. The split second after the collision, the 2 masses have become 1, and I'm just going to call that V3. And at time 4, they come to rest. The spring is compressed. So V4, this is our final state. Okay, so I always approach these problems the same way. I break them up into time intervals. For a typical ballistic pendulum problem, my time 1 would be the split second before the collision. My time 2 would be the split second after the collision. And my time 3 would be some later final state when the pendulums come to rest. But in this problem, I have 4. I have something happens before, then I've got the collision, and then I've got something happening afterwards. So any type of ballistic pendulum problem, and again, ballistic pendulum meaning that there's a collision and either something happened before the collision or something's happening after the collision that you have to work through. Break it up like this into the different time zones. Now, what are we looking for? We're looking for this initial height. And so that's something in condition 1, at time 1, right? So how are we going to get there? Well, we're going to start at the end and work backwards. So we're going to go from time 4 to time 3. And how are we going to go from 4 to 3? We're going to use energy conservation. Because there are no collisions, there's nothing happening in there that would prevent us from using energy. The energy at time 4 should equal the energy at time 3. We've got nothing to dissipate it. No external forces, no friction. So the energy at time 4 should equal the mechanical energy at time 3. At time 4, all of our energy is in the spring. Nothing's moving and no heights are changing here. So the only energy we have is elastic potential energy. And at time 3, the only energy we have is kinetic energy. It hasn't changed in height. The spring is not compressed at time 3. So we have 1/2 m3 v3 squared. So my velocity at 3 let me plug in some numbers. K is given, delta x is given, the compression of the spring, and the mass is, they've stuck together and they're both 10 kilograms, so we have 20 kilograms now, and the velocity is 2.01 meters per second. So the two things have stuck together, and immediately after the collision they're moving at 2.01 meters per second. So we've worked from time 4 to time 3. We've figured out what V3 is. Now we have to go from 3 to 2 so we can figure out what the velocity of cart A is at time 2. And once we know that, then we can go to time 1 and find the height. So we've gone from 4 to 3 using energy. We have to use momentum conservation to go from 3 to 2 because we're going through a collision. So this is using energy. And to go from 3 to 2, we have to use momentum. And to go from 2 to 1, we can use energy again. No collisions there. So the momentum at time 3 has to equal the momentum at time 2. At time 3, there's only one thing, the mass of 3 times the velocity of 3. At time 2, we have two things. We have the mass of A times the velocity plus the mass of B, that's an M, the mass of B times its velocity, but it's not moving. That's 0. So we have the velocity of A at time 2 is m3 v3 over m2. (20) times 2.01 over 10. 4.02 meters per second. And now we're going to go from 2 to 1 using energy conservation. So the mechanical energy at 2 should equal the mechanical energy at 1. We've got no friction or external forces. At time 2, the only thing that has energy is mass A, and it's moving. And at time 1, mass A is the only thing with energy, and it's gravitational energy. The masses cancel, and we get the height is the velocity squared over 2g. I got 0.825 meters. So very important with these types of problems that mix a collision in with things that you would normally use energy to solve for. Don't fall into the trap of trying to use energy all the way from the initial state to the final state, because if there's a collision in between, chances are mechanical energy is not conserved through that collision. In this case, we know for certain it's not, because the two objects stick together. So you have to break it up. You can use energy to get right to the split second before the collision. You can use energy from the split second after the collision to the end, but you can't go through the collision with energy. You've got to use momentum to get through the collision.